For Math 8 today, we are starting a new module. This is Module 6, and it's over linear relationships. So we're going to actually just start to talk about linear relationships. These are just lessons 1 and 2, and we're going to start with some situations, so some scenarios. So read with me these first 3 problems. It says, Asia is training for a 10K road race that will take place in October. She starts her training in July and runs every weekend. On her first run, she ran at a constant pace and covered 5.5 miles in 60 minutes. On her last run before the race, she also ran at a constant pace, but this time covered 10.2 miles in 1.5 hours. What were her speeds in miles per hour? That's going to be important. We want it to be miles per hour, so I don't want to say minutes. I'm going to convert this to hours. So in miles per hour on her first and her last run, and therefore what was her unit rate? Okay, here's her first run. It was 5.5 miles in 60 minutes, but I want to convert that to hours. So I'm going to put 5.5 miles per 1 because that's miles per hour. So when you divide that out, 5.5 divided by 1 is just 5.5. So her unit rate is just going to be 5.5. This is miles per hour, and that's what the unit rate is. It's how many divided by 1. Okay, so her second pace, let's look at that. It was 10.2 miles in 1.5 hours. So 10.2, but this time in 1.5, I'm going to put 1.5 because that was in 1.5 hours. Okay, I'm going to divide this out to get the unit rate. So 10.2 divided by 1.5, I don't know what that is, so I'm going to use my calculator. 10.2 divided by 1.5 is 6.8. So she was going much faster on the second run. She was going 6.8 miles per hour. Okay, so those are the speeds and they are the unit rate. So now let's go down to number 2 where you're going to start to write equations. Okay, so we want to write an equation that represents the function of time for her first run and her last run. So we're going to write 2 different equations based on her different speeds. And we're going to use the form y equals kx, where k is our constant or our unit rate. So this k that's our constant is going to be 5.5 in the first one, and it's going to be 6.8 in the second one. So it's going to be y equals 5.5x and y equals 6.8x. And then it wants to know, what exactly does x represent? What does y represent? Why are we writing it like y equals a number x? What does k represent? So let's just start and see. Number 1 would definitely be y equals 5.5x. And that means she ran at a constant speed of 5.5 miles per hour. So when it says what does k represent? K represents her speed. Okay, so k represents the speed. X and y, x would represent she runs a speed of 5.5 miles per hour times how long did she run? So x is going to represent the time, the amount of, and actually it's specifically hours because remember we converted minutes to hours. So x is time. So if I said she ran 5.5 miles per hour for 2 hours, you would be able to tell me exactly the total number of miles she ran. So that means that y is going to represent the distance, which specifically that distance we're talking about is in miles. So you could plug any number you want for x representing the time. Say I ran 5 hours. You could plug in 5 and multiply it by 5.5, and I would be able to tell you how far I ran in miles. So that's what the speed is, time is the x, distance is the y. The second equation is exactly like this one, but this time it's y equals her second speed, which was 6.8. Okay, so now we can go down here and use this information to plug in numbers. So a 10K road race is approximately 6.2 miles. So if I'm wondering miles, distance, I can plug that in and see how long it would take. So that's actually what they're asking. If Asia ran at her beginning pace, how long would it take her to finish the road race? How long would it take her if she had her ending pace? use the equation, or you could make a table of values. So anytime you have an equation, that's going to be the easiest path. So let's start with the first one, if Asia ran at her beginning pace. So that would be y equals 5.5x. And we're plugging in 6.2 for miles. And remember, miles is going to be our y. So instead of y, I want to plug in 6.2. Okay, and the reason we did a whole big unit right before this on equations is because you should know, in order to get x by itself, you would divide both sides by 5.5 in order to get what x is equal to. So 6.2 divided by 5.5 is a little bit over 1.127. So I'm going to call it 1.13. I'll bump the 2 up to a 3. So 1.13. And this is about 1.13. And what is x? X, again, if you forgot, is our time. So that means it would have taken her a little over 1 hour to run 6.2 miles. So a little over 1.13 hours. Okay, and then what if she did it at her ending pace? So our ending equation was y equals 6.8x. And again, the race is 6.2 miles long, which is our y. So we're going to plug that in for y, and we're just going to solve the equation. To get x by itself, you would divide both sides by 6.8. And I don't know what that is, but I'm going to use my calculator. 6.2 divided by 6.8 is under an hour. It's a 0.1 about. It's approximate, but I'm going to say it's about 0.91 hours. So at her original pace, which was a little slower, it would have taken her to do 6.2 miles a little over 1 hour, but at her faster pace, it's going to take her a little under 1 hour, not even one whole. Okay, this leads us into the graphs. So here are her first run and her last run represented on a graph. Notice that both graphs start at the origin because at 0 hours she'd gone 0 miles, so she starts at 0, 0. That makes it proportional. In order to be proportional, it needs to go through the origin and be constant or straight. So it starts at the origin and goes constant in a straight line. So look at the rate in which each line is increasing. So this line is at a different slope than this line is. So what we have learned today is that we are representing proportional relationships as descriptions, as equations, as a table. We didn't actually set up the table yet, but we could have, and we will later, and in these two forms of graphs. Okay, turn to the next page, and we're actually going to look at a graph. So the graph below shows the relationship between the distance an airplane has covered and the amount of time it has been flying. So what is the speed of the airplane in miles per hour? So we need their miles per their hour. So we need their y over their x, because if you guys can see this, miles is up the y-axis. So miles first and then hours. So if we go to 1, that's going to be really hard to tell the exact number. So I am going to try my best, but I would say we're going to have to estimate. So this is going to be about. So I would say this is 200, 400, 600. I think we could probably say 500 is in the middle. So maybe 550. I'm not sure if you guys are okay with 550, but I'm going to say that this dot is about 550 in 1 hour. So what speed? It's going about 550 miles per hour. Okay, what's the rate of change? Okay, well, the rate of change just means how many miles per hour is it. So the rate of change would be 550 because that's miles per hour. And so what is the slope? Guess what? Every 550 I go up, I'm going to go over 1. I would go up about 550 more and go over 1 more. I'd go up about 550 more and then over 1 more. And it would always land on our line. So the slope of the graph is actually 550 per 1, or just 550 is fine. And then what equation would this be? It would be y equals 550x, because this is the unit rate or the slope, same thing. Okay, let's look at problem 3. It says 4 representations are shown below. 3 of these 4 boxes that you guys see here match. Which one does not belong? Explain. So I would love for you guys to push pause on the video right now and look really closely at all 4 of these boxes and see if you can figure out which 3 match and which one would be wrong, and then push play and see if you are right. Okay, I hope you guys looked at your graph and you saw that it was going up 1 per over 2. So up 1 over 2. See how it goes up 1 and then over 2. So this is up 1 over 2. So the rate is 1 over 2. A caterpillar, let's look at the description. A caterpillar moves at a constant speed of 1/2 inch per second. So let X represent the time in seconds and Y represent the distance traveled in inches. Let's go back over here and look. Y is the distance and X is the time. So let's look. Distance. It went 1/2 an inch per 1 second. Another 1/2 an inch per another 1 second. Another 1/2 an inch for another 1 second. So this one is the same. 1/2 per 1, 1/2 per 1, 1/2 per 1, which is the same as up 1 over 2. So these two are so far the same. Let's keep looking. Our table shows X and Y at 2, 1. So if I were to put a dot at 2, 1, it would be right here. Then I might put a dot at 4, 2. Which would be right here. Notice that's still on my graph. 6, 3, yep. So these are all 3 correct so far, matching. Okay, Y equals 2X. Well, what you noticed up here is every single rate of change had 550 in it, and our equation also had 550 for K. So down here, if this one's 1/2, this one's 1/2, this one would also be 1/2. 1/2 of 2 is 1, 1/2 of 4 is 2, 1/2 of 6 is 3, 1/2 of 8 is 4. Our equation should not have been Y equals 2X. It should have been Y equals 1/2 X. So this is the one that is wrong. Okay, let's look on the 3rd page. Problem 4, it says water flows at a constant rate out of a faucet. Suppose the volume of water that comes out in 3 minutes, is 10.5 gallons. Find the volume of the water out of the faucet after 0 minutes, after 1 minute, and after 4 minutes. So all we know so far is that in 3 minutes, it's already up to 10.5 gallons. So we're going to go in time to 3 minutes, and then in gallons of water up to 10.5. So, and we're going to put a dot. That's the only information we know right now. So if every 3 minutes it flows 10.5, I'm going to go ahead and say, I'm going to write that down. So 3 minutes per every 10.5 gallons. All right, so after 0 minutes, let's say we haven't turned on the faucet, 0 minutes, how much do you think has come out of the faucet? I hope you said 0, because if I haven't turned it on yet, there hasn't been any water come out of it yet. Okay, then it says 1 minute. Well, I know that it's coming out at a proportional rate. So I know I really should not be drawing this in without a ruler, because my line's not going to be straight, but that's okay. I know that it's going to be constant, which means it's going to have a straight line. So I could go in 1 minute and I could go up to see about where that's at. But a better way to do it would be to find the unit rate. If it's 10.5 gallons per 3 minutes, actually I'm going to rewrite how this looks. I'm going to write it like this. 10.5 gallons in 3 minutes. I'm going to first find the unit rate by dividing that, because then I will know how much it is per 1 minute. 10.5 per 3, 10.5 per 3, which means 10.5 divided by 3 is 3.5. So now I know my rate, which is going to help me because I know that it's emptying, or sorry, it's coming out at a rate of 3.5 gallons per minute. So now I can go in 1 minute, it would be 3.5. Ooh, I made a pretty straight line. In 2 minutes, it would be whatever another 3.5 is, which should have been 7. Okay, so my line's not terrible. But so it's asking 0 minutes, it would be 0 gallons. 1 minute, it would be 3.5 gallons. And then after 4 minutes, we can just keep multiplying by 3.5s. So 4 minutes times 3.5 is our rate, 14 gallons. Okay, so we're going to write a linear equation to represent the volume of water that comes out in any t number of minutes. So I would normally tell, they want us to use v. I would normally say, well, it's y equals 3.5x. But for some reason, this particular problem wants us to use t for minutes and v for volume of water. So I'm going to use the total volume of water is 3.5 gallons per t minutes, which is time, probably. So here's your equation. Whatever your unit rate is goes here. Total volume or whatever you're talking about is here, because that's what it's equal to. And you multiply by the amount of time that you're talking about it filling up or emptying out or whatever it's doing. Okay, graph the equation. We already graphed it. I did. I hope you guys did. Will it be a straight line? It is absolutely yes, because the amount of water is constant. So if we were talking about a different number each time, 3.5 sometimes and 8 another time and 1 another time, it would not be a straight line. But because the amount of water is constant, and you can even put that it's constant at 3.5, that is what specifically makes it a straight line. Every 1 more minute is another 3.5 gallons. Another minute, 3.5 more. Another minute, 3.5 more. It's always that constant same rate. So what is the slope of the graph? I hope you guessed it. It's 3.5, because that means you're going to go up 3.5 per over 1. You're going to go up 3.5 over 1. Up 3 more 0.5 over another 1. Up 3.5 over 1. So the steepness or the slope is up 3.5 per 1. And what does it mean as a unit rate? It means that 3.5 gallons of water flow each minute, each 1 minute. Okay. According to your graph, what is the volume of water out of the faucet after 2 minutes? So according to our graph, 2 minutes is 7. 2 minutes, 7 gallons. All right, what about according to your graph, how long would it take for 15 gallons to flow? So I would go up here to gallons, and I'd go to 15, and I'd go out and see where we're at. And I did not continue that the whole way, so I need to keep going. We need to go up 3.5 more over another 1, 3.5 more over another 1, and then try to go ahead and make your line as straight as possible. So if it's saying 15 gallons, I'm going to go up here to 15 gallons, straight out, and that's not going to exactly be at a specific number. So I'm going to guesstimate it's going to be a little more than 4 minutes, because if I go straight up there, that's where it hits at 15. 15 gallons, a little bit more than 4 minutes. So I'm going to say about over, I'll even say a little over 4 minutes. Okay. Let's look down here at the bottom with problem 5. It says, Nia and Trey both had a sore throat, so their mom told them to gargle with warm salt water. I don't know if your parents have ever told you that. Nia mixed 1 teaspoon of salt with 3 cups of water. Trey mixed half a teaspoon of salt with 1.5 cups of water. Nia tasted Trey's salt water, and she said, I added more salt, so I expected that mine would be more salty. But gotta look on the back, they taste the same. Explain why the salt mixture would taste the same. What is the ratio for each one, and are they equal? Are they equivalent? You could use a table if necessary. So I'm going to suggest we just set up 2 equations. So if we know that Nia mixed 1 teaspoon of salt with 3 cups of water, That means she had 1 teaspoon per 3 cups of water. And this is salt, and this is water. Okay, and I'm going to flip it because I always want to know per 1. So I'm actually going to say 3 cups of water per 1 teaspoon of salt. And this is Nia. Okay, now let's do Trey's numbers. And remember, I'm going to put water on top and salt on bottom. So water for Trey is 1.5, 1.5. So 1.5 water, and that's cups, per half teaspoon of salt. So 0.5 teaspoon of salt. Okay, this one is already in unit rate because it's 3 per 1. This one is not per 1. I need to divide these out so that it equals per 1, and then we'll see what we get. So I'm going to take 1.5 and I'm going to divide by 0.5. So 1.5 divided by 0.5 is actually 3. So that would be the equivalent to 3 cups of water for Trey per 1. Since I divided it, it's always out of 1. Unit rates mean they're out of 1. So look at this. Nia's and Trey's are actually the same because 3 cups of water per 1 teaspoon of salt is the same as what he came up with if we were to get it into a unit rate. So when you look at the back and it says explain why they taste the same, it's because their ratios are the same. So this are they equivalent bit is yes. We just proved it on the other side. Okay, number 2 says find an equation that relates S's, I guess, I don't know, the number of teaspoons of salt with W's, the number of cups of water for both mixtures. So here's our equation. They're both y equals 3x. And that's because per every, here, we can just look at it right here. Per every 1 teaspoon of salt, we added 3 cups of water. 3 cups per 1 teaspoon of salt. So that would mean 3 per every 1. So what we're going to say is we need to put water on this graph. We're going to put water in cups, and then we're going to put salt in teaspoons. And it says draw a graph. What label did you put on each axis? We put salt on our x-axis. And then we put water on the y-axis. Will the origin point on your graph, will the origin be a point on the graph? So we're asking, is 0, 0? And the answer to that is yes, because if we haven't made any yet, if we haven't made a salt mixture, then we have 0 salt added for 0 cups of water. So we're going to start with nothing. However, if we have 1 teaspoon of salt, we're going to have 3 cups of water. So my next dot will be here. If I had another teaspoon of salt, I would have to have another 3 cups of water. So that dot would go here. Another teaspoon would be another 3. So every up 3 is over 1. Every up 3 is over 1. 3 cups of water, 1 teaspoon of salt, and so on. So yes. And why is because at 0 cups of water, we have 0 teaspoons of salt. That just means we haven't done anything yet. Okay, what is the slope of the line? Obviously the slope is up 3 per over 1, up 3 per over 1. Actually, I never drew my line in. Let's go ahead and draw my line. Oops, and I'm going to put an arrow at the end because it would keep going. If I were to keep adding more and more cups of water, I'd add more and more teaspoons of salt. So this is going to be an arrow. So this keeps going. The slope of the line is 3. Or if you want 3 per 1, because it's up 3 over 1. That's how steep it is. What does the line mean as a unit rate? It means 3 cups of water per 1 teaspoon salt. Okay, I would really like for you guys to push pause and try the check for understanding on your own. If you're absolutely not ready yet, I understand. I will do this with you, but I would encourage you to right now push pause and try the check for understanding on your own. Okay, if you weren't quite ready to try it on your own, this is the part that I need to see your canvas. You need to take a picture of this section. So if you did it on your own, that's great. I want you to check and make sure you did it correctly, but this is your actual assignment that I need you to upload a picture of to Canvas, this check for understanding right down here at the bottom. All right, so at the grocery store, sliced deli meat is on sale for $11. You get 2 pounds. What is the cost per pound? That's per 1 pound. So I need to divide it out. So if it's $11 per 2 pounds, I need to get a unit rate. I need to divide 11 by 2 to see that it's 5.5 or $5.50 per pound. So 5.5 means $5.50. Go ahead and add that at 0 per 1 pound. Okay, so what is the cost per pound? $5.50 per 1 pound. Write an equation to represent the cost of Y sliced turkey deli meat measured in X pounds. That would just be Y equals 550X. And at this point, you can just do 5.5x because we're not necessarily talking about money in our equation. It's about money, but when you write it in an equation, you don't need the extra zeros or anything like that. Okay, let's draw a graph of this situation. If we don't buy any turkey, we don't pay any money. So it would be 0, 0. Okay, if we need to label these two. This is the cost. This is the pounds of turkey. All right, so every 1 pound cost us $5.50, and I know this didn't copy very dark. It's kind of hard to see, so just look closely. 1 pound of turkey would be 1, 2, 3, 4, 5.5. Okay, then go over 1 more pound would be half. 1, 2, 3, 4, 5. Another 1 pound up 1, 2, 3, 4, 5.5. Another pound, half, 1, 2, 3, 4, 5. Okay, so that's really hard to see, and my line is definitely not going to be very straight. Sorry about this. Whoop, it's close enough. But every 1 pound is $5.50 more dollars. 1 pound, money, pound, more money. Okay, so we graph the situation. What is the meaning of the slope? The slope is 5.5 per 1, and that means we went up 5.5 per every over 1, which means if you're asking about the actual meaning, it means each $5.50 will be 1, I guess, more pound of turkey. Okay.